Florence-2 is arguably one of the coolest computer vision models of 2024. Released by Microsoft under MIT license, it is capable of image captioning, OCR, object detection, and much more, and all of that within a single model that can easily run on consumer-grade hardware, edge devices, or even in browser. However, just like other foundational models, Florence-2 might need a little bit of fine-tuning to perform well on specific domains. So today I'll show you how to fine-tune it on your own custom object detection dataset. At the end of the video, we'll also compare Florence-2 against other top computer vision models right now. This is definitely one of the most technically advanced tutorials that have ever appeared on this channel. I myself learned a lot while preparing it, so buckle up because we have a lot to cover. As usual, I prepared a Google Colab that you can open in a separate tab and follow along. The link to the notebook is in the description below, but you can also find it in our notebooks repository, where we store all notebooks related to our YouTube tutorials. Scrolling down a bit, we see fine-tune Florence-2 on object detection dataset. We click Open in Colab button. The tutorial is designed so you can fine-tune Florence-2 on your dataset for free using Google Colab with NVIDIA L4 GPU, but if you have powerful enough hardware, you can also run it locally. You will need about 20 GB of VRAM, probably less if you adjust the hyperparameters values such as batch size. More about that later in the video. Before we start experimenting with Florence-2, we need to make sure our environment is properly configured. Let's start with setting up our access keys. To download the pre-trained Florence-2 model from Hugging Face, we need to generate our HF token. To do this, we open our Hugging Face settings or click the link in the notebook. There, we click the New Token button to generate it. To download the object detection dataset compatible with Florence-2, we'll also need Roboflow API key. Similarly, we open Roboflow settings or click the link in the notebook. Here we can just copy our API key or generate the new one. When we have both keys, we go back to Google Colab and click the Secrets tab marked with the key icon. You can find it in the left side panel. There we set both values. Ultimately, your side panel should look just like mine. If you are executing the code locally, simply set both values as environment variables or write them down into your .env file. The next step is to make sure our Google Colab has GPU acceleration. To do this, I run NVIDIA SMI command. The result of the command should look just like mine. If you see something else, click Runtime and then select Change Runtime Type from the dropdown. Then, when the pop-up appears, select L4 and click Save. We quickly download a test image that we'll use in a second to test Florence-2 model. And finally, we need to install a few more dependencies that are not part of base Google Colab environment. We install transformers, flash attention, team, and anops to load our model, as well as peft to configure LoRA. I'll tell you a bit more about LoRA later in the video. Additionally, we install Roboflow to download our dataset from Roboflow Universe, and Supervision, which we'll use among other things to visualize prediction and to benchmark our fine-tuned model. Let's start by loading the pre-trained Florence-2 along with the tokenizer into the memory. A tokenizer is responsible for converting images and text into a format that the VLM model can understand. As I mentioned, the Florence-2 is quite small. The base version has only 230 million parameters, so this should take only a few seconds to download the weights and load them into the memory. In the meantime, I opened the right Google Colab panel so we can track the VRAM usage. For starters, I'll use the pre-trained model and show you a few prompting examples with different vision tasks. Out of the box, Florence-2 offers over a dozen different vision tasks, but allows you to add new ones if needed. To let the model know which task to perform, we start our prompt with the task name enclosed in the angle brackets, and then, depending on the task, we provide optional text prompt. Let's start with object detection. In this case, our entire prompt is just OD in angle brackets. First, image and prompt goes through the tokenizer, where both are converted into sequence of tokens, which then go through the model where the response is generated. Finally, using supervision package, this response is converted into a set of bounding boxes, along with class names that you see on the output image. 4 objects were detected. We can print detections to get more details. We see the hat class here and its corresponding visualization. We can also explore the raw text generated by the model. We'll talk more about it in a few minutes when I'll cover the format of custom dataset, the response format, and the dataset format for each image is pretty much the same. The next task supported by Florence-2 is image captioning. We have 3 types to choose from. We have caption, detailed caption, and more detailed caption. I love those creative names, by the way. Of course, depending on the chosen task, the image description will become more and more detailed. In this case, the tokenization is identical, but we get plain text as result, no additional parsing as needed. In the image, we see a person wearing a bag and holding a dog, etc. The last task I'll show you is caption to phrase grounding. This task involves associating specific phrases in the caption with corresponding regions in an image. As our caption, we'll use the text resulting from the previous inference. This time, our prompt is task name in angle brackets and the following caption. The response is once again bounding boxes, but each box is paired with phrase from original caption. If you want to experiment more, you can use Florence-2 Hugging Face Space. The link is in the description. Now it's time to talk about the data format required to fine-tune Florence-2. Our dataset is a directory with 3 subdirectories: train, test, and validate. Each subdirectory has identical structure containing images, for example, image_1 PNG, image_2 PNG, and a annotation file. In case of Roboflow, it is called annotations.json.l. Each line of such file is separate JSON structure. When we load such a line as Python dictionary, we have 3 keys: image, prefix, and suffix. Those of you who watched our Polygemma tutorial probably have deja vu, but don't worry, there are some differences. I'll get there in the moment. The image key obviously points to the image associated with the annotation. Let's say that in our case, it's image_1 PNG. The prefix is the prompt that we want our model to react to. In our case, it's plain OD in angle brackets, and the suffix is the expected response. So let's assume we have an image and a detection that we can describe with bounding box with coordinates x1, x2, y1, y2. The whole image has dimensions w by h. We can then write the coordinates of our bounding box as an array, arranging them in appropriate order. Next, we normalize them and divide them by appropriate image dimensions. Finally, we multiply them by 1000 and round them to integers. Ultimately, the box coordinates have values between 0 and 999. To write them in the way understandable for Florence-2, we prefix each coordinate with log underscore and enclose them in angle brackets. In front of the whole bounding box representation, we place the name of the class. If there are multiple boxes in the image, we simply place their definitions one after another. The order of the bounding boxes does not matter. Starting this week, all datasets on Roboflow Universe can be downloaded in format compatible with Florence-2 object detection. In this tutorial, I will use Poker Cards dataset, which is part of Roboflow 100, a set of 100 object detection datasets that you can use, for example, to benchmark zero-shot capabilities of models like Polygemma, Florence-2, or YOLO World. Of course, you can choose any other object detection dataset. There are over 500,000 of them on Roboflow Universe. Once you're ready, click the Download Dataset button, and when pop-up appears, pick Florence-2 from the dropdown, check Show Download Code, and click Continue button. After a few moments, a code snippet will be generated, which we simply copy and paste into Google Colab. We press Shift plus Enter, and after a few seconds, the dataset should be downloaded to our machine. We confirm this by opening Files tab in left side panel of Google Colab. The dataset consists of 3 subdirectories: train, test, and valid. Each of them contains images and annotations JSON-L file. Now we can use Linux head command to display the first 5 lines of this file. We can see that it has the structure we described a few minutes ago. Now it's time to prepare our PyTorch data loaders, which we'll use to feed our dataset into the model during the training. Unlike most of our tutorials, where this step is completely hidden under high-level API of the library, like in case of YOLO V8, here we have to do everything ourselves. By the way, if you have any questions about the dataset format, training process, or the model in general, don't miss out on our community session that will happen this week, where we are going to talk about Florence-2. So if you have any questions, leave them in the comments and I'll do my best to answer them during the upcoming live stream. The details about specific day and time are in the description below. Drop by and say hi. We create new class detection dataset, which inherits from PyTorch dataset. In this class, we must implement 2 functions, len and getItem. The first returns the size of the dataset, and the second returns a dataset element at specific index. Our detection dataset will take 2 arguments, the path to JSON-L file and the path to directory containing images. Inside, we open the JSON-L file, read it line by line, and parse each line as separate JSON. As a result, we get a list of Python dictionaries, where each dictionary has 3 keys: image, prefix, and suffix. We save the list in entries field. Now in the len implementation, we simply provide the length of the list, and in the getItem implementation, we retrieve the value from entries list at specific index and load the associated image. Defining data loaders is much simpler. We simply import the data loader class from PyTorch and initialize 2 objects, one for training set and one for validation set. The only additional thing is to define a collectFn callback. Its job is to collect a list of samples into batch by combining individual elements into tensors. Now our dataset is ready to be used during the training. Although, as I mentioned, Florence-2 is a relatively small model, and with 270 million parameters, it can easily fit consumer-grade GPUs or even edge devices during the inference. Training this model requires a lot more resources. More than 20 gigabytes of VRAM we have available in L4 Google Colab instance. As I always design my tutorials so you can easily reproduce them for free, for example in Google Colab, it's time to get a bit more creative and use LoRA. Configuring LoRA for transformers models is quite straightforward, and we will use PEFT library to do it. We first define LoRA config, setting both rank and LoRA alpha to 8. Then we pass our previously initialized model along with configuration to getPEFT model function. As a result, we get a new model that will allow us to leverage LoRA during the training. Finally, we use the print trainable parameters method, showing us the level of optimization. We see that our base model has about 270 million trainable parameters, while the LoRA version barely has 2 million. Finally, it's time to fine-tune our model, but before we will do that, let's run an inference on a subset of validation set using pre-trained model. This will allow us to confirm that our data loaders are working properly and check how pre-trained Florence-2 model handles those images. We'll use it as a baseline score for our fine-tuned model. Inside the short for loop, we iterate over a specified number of samples from the validation set and run selected model on them. Here we use pre-trained model, but during the training we'll use the same code to visualize the fine-tuned model. The code you see here is mainly for visualization purposes. It takes inference result and display them in nice HTML form. Quickly looking at the actual results, we see that the model returns bounding boxes the size of entire image, with class names probably related to the background. We see classes like furniture, table, bed, or chair. Not a word about playing cards. Well, let's see if the fine-tuned model will be capable of detecting them. The next step is to define our training loop. It roughly consists of 3 elements. The first is the initialization of the optimizer. In this case, we use AdamW. An optimizer is an algorithm that adjusts weights values of our neural network during the training to minimize loss function. AdamW is a variant of popular Adam optimizer that incorporates weights decay, which helps to prevent overfitting. We also initialize our learning rate scheduler. Learning rate is a hyperparameter that controls the step size of our optimizer, and learning rate scheduler adjust that step size to improve the performance. Next, inside the for loop, we iterate over epochs. An epoch is a single pass through entire training dataset. And inside this loop, there are 2 more. The first one iterates over batches of training set. Each batch is passed through the model, and then the weights are updated using backpropagation. Of course, it's a little bit more complicated, mainly because of our use of LoRA, but let's just keep it simple. We also calculate our training loss. After each pass through the training set, a second loop iterates over batches of validation set. This time we don't calculate gradients nor update weights, we only calculate the validation loss. Finally, it's time to trigger the training loop. In my case, I set it for 10 epochs, and with dataset of about 1000 images, the whole fine-tuning should take about 40 minutes. Let's use the magic of cinema to speed up the process. By the way, I really like how, thanks to HTML visualization, we can compare how quality of predictions improves during the training. Okay, let's take a look at final results. Now that our model is trained, it's time to benchmark it. Since we fine-tuned it for object detection, I decided we'll benchmark it like any other object detection model. We'll calculate the MAP and confusion metrics using previously installed supervision package. The first step is to gather our ground truth and detections for each image in the test set. Due to the inconvenient data format, we'll need to write a little bit more code than usual. First, we need to parse our dataset to find the list of unique object detection classes. We need this to build class name to class ID mapping, as algorithms like MAP and confusion metrics operate on class IDs, not class names. Inside the for loop, we make predictions using newly trained model and then convert our ground truth and predictions into matrix representation needed to calculate those metrics. An interesting thing that is quite specific to models that generate sequences of tokens and not happening in traditional object detectors is the need to filter out objects with misspelled class names. Just like LLMs, Florence-2 generate a sequence of tokens, and sometimes there is an error in that sequence that result in misspelled class names. Here's an example. We have 2 cards with incorrect class names. The first one is quite subtle. We have Jack of Spade, and according to our class list, it should be Jack of Spades. The second one is 10 of SP clubs, and it should be either 10 of spades or 10 of clubs. So before we calculate our metrics, we need to filter out detections like this. Now that we have our two lists, supervision will do most of the heavy lifting. Ultimately, we achieved an MAP of 0.75. MAP is a metric used to evaluate object detection models. It measures the average precision across different recall thresholds. By the way, we have a great article on our blog about MAP. The link is in the description. For comparison, I performed an identical experiment, fine-tuning YOLO V8S on our poker cards dataset, achieving an MAP of 0.9 there. Difference is quite significant, but generative models are closing the gap really fast. Now, let's take a look at confusion metrics. Confusion metrics is a table that summarizes the performance of classification or detection algorithm, showing you the amount of correct and incorrect predictions for each class. If you want to learn more about confusion metrics, we also have a wonderful blog post covering this topic. The link is in the description below. There are 52 classes in this dataset, so it's quite hard to see the specific, but right away we see a large accumulation of values on matrix diagonal. This means that the model correctly located and classified those objects. Generally, there were only few class mix-ups and not many false positives. Those are the cases where the model detected an object that was not there. However, there are a lot of false negatives, meaning cases where the model did not detect the object that was in the image. One of the reasons for that could be our filtering of detections with misspelled classes. Maybe if we would apply different handling of that issue, the score could be actually higher. Overall, I'm very happy with the result. For VLM of this size and with such a broad range of capabilities, getting a result like this is quite impressive. Not to mention, it was actually quite easy to train this model. I have no doubt that we are closing in to the moment where fine-tuned VLMs and traditional object detectors will be capable of getting similar accuracy levels. Before we wrap it up, I decided it would be a cool idea to put things into perspective and compare Florence-2 to other top computer vision models. Let's take a look at Florence-2, Polygemma, Lava, GPT-4 Vision, YOLO World, Grounding Dino, and YOLO V8. As I mentioned today, Florence-2 supports over a dozen of computer vision tasks, including captioning, detection, segmentation, grounding, and OCR. Polygemma, the model I showed you last month, also tried to unify as many tasks as possible within a single model. Lava and GPT-4 Vision can handle captioning, VQA, and OCR, but unfortunately no object detection. YOLO World and Grounding Dino run zero-shot detection, and YOLO V8 does detection. Sure, YOLO V8 can perform segmentation or pose estimation, but then you need to load a second model. Here I'm interested in how many tasks can be performed by a single model. As for the license, Florence-2 and Grounding Dino have fully open source licenses. Lava in theory as well, but in practice only the code is under Apache 2. The model was trained on ChatGPT output, so it cannot be used in enterprise settings. Polygemma requires license acceptance, but then we can use it even in enterprise projects. The next category is self-deploy. Of course, GPT-4 Vision as fully closed model behind the API does not give us this possibility. As for the rest, the amount of $signs next to each model maps to the hardware power we need to deploy it. Florence-2, YOLO World, and YOLO V8 can be easily deployed even on edge devices. Polygemma and Grounding Dino will easily fit on consumer-grade GPUs, and Lava, at least without any optimization, will require the most of VRAM. Next up is speed. The values in table correspond to measurements for batch size 1 on NVIDIA V100 and are largely correlated to model size. The fastest is, of course, YOLO V8. By the way, similar values can be achieved for most modern YOLO architectures and some real-time transformers like RTDTR. YOLO World can also run in real-time, and the remaining models are about 1 up to several frames per second. In summary, if you need your model only for object detection and you really care about the speed, choosing one of popular YOLO-based models is probably your best bet. However, if you need your model to detect classes from different datasets, like for example some classes from base Coco dataset plus classes from your custom dataset, models like Florence-2 or Polygemma can do it with ease. And that cannot be said about traditional conv-based models like YOLO V8. If you need zero-shot detection, Grounding Dino and Florence-2 are my favorites, and if you need to run multiple tasks like captioning, OCR, and object detection, I'd choose Florence-2 or Polygemma. I hope you learned a lot today, just like I did. I still have a lot of ideas for Florence-2 tutorials. I could tell you a little bit more about its zero-shot capabilities or show you how to fine-tune it on different computer vision tasks. Let me know in the comments if you're interested in Florence-2, and if so, what would you like to see? Also, don't forget about our upcoming community session where I'll answer all of your questions during the live stream. The details about the exact day and time are in the description below. Meanwhile, that's all for today. If you liked the video, make sure to like and subscribe, and stay tuned for more computer vision content coming to this channel soon. My name is Peter, and I see you next time. Bye.